diving right in. pH and pOH are they're ways of describing acidic and basic solutions, and they're based very, very strongly on water. P of anything, lowercase p, it's always lowercase, is just the negative log of that thing. Negative log base 10, I should specify. So pH is negative log of the concentration of H+. pOH is negative log of the concentration of OH-. And, like I said, they're based on water. If you take the negative log of the auto-ionization expression, you get pKw is equal to negative log of H+ times OH-. And thanks to the magic of logs, that means that pKw is equal to negative log H+ plus the negative log of OH-. I'm leaving the negative in there because it makes it easier to see that we're talking about pH plus pOH. Negative log of H+ is pH, negative log of OH- is pOH. So pKw is pH plus pOH. And of course, pKw is equal to the negative log of 10 to the negative 14th at room temperature, or 14. So pH plus pOH is 14. And once again, we see pH equals pOH equals 7 when it's neutral. But this also gives us a handy way of translating back and forth between pH and pOH, which is something that we'll have to do occasionally in working with acids and bases. Because, of course, bases mostly produce OH-, acids mostly produce H+. But we, humans, work in pH just because we are foolishly consistent in that way. But, just 14 minus pH gives you pOH. 14 minus pOH is pH. So 14 minus whatever gives you the other one. Okay, let's move on. This should be a review for you. Now we finally start talking about acid and base equilibria with Ka and Kb. One of the methods we have for measuring the strength of our weak acids and bases. Ka and Kb are just equilibrium constants. Nothing fancy about them. It's just that Ka is the equilibrium constant for the dissociation of an acid, and Kb, or ionization of an acid, and Kb is the equilibrium constant for the dissociation or ionization of a base. And this shouldn't come as too much shock for any of you guys. I already covered acids and bases quite extensively back in Chapter 13. I included a lot of examples of those. I just didn't call them Ka or Kb. But this is a form of this equilibrium expression you're going to be seeing a lot. Ha dissociates or ionizes into H plus and A minus. So Ka equals H plus times A minus divided by Ha. Similarly, BOH dissociates or ionizes into B plus plus OH minus. So Kb equals B plus times OH minus divided by BOH. But because we're not working with Arrhenius, we're working with the Bronsted-Lowry definition, there is another possibility for that base equilibrium, the equilibrium for the base. So instead of having a hydroxide donor, you could have a proton acceptor. The Kb looks slightly different, but it's fundamentally the same. B plus H2O goes to form Hb plus or BH plus OH minus. And this is just a generic form of the ammonia reaction. If ammonia was B, it would be NH3 plus H2O makes NH4 plus OH minus. Okay. You're just tacking an H plus onto the base. But the equilibrium expression, Kb, it looks very similar. BH plus times OH minus over B. Okay. It's just, accepting a proton instead of releasing an OH minus. You're going to be seeing these a lot. We're going to be doing a lot of ice tables with acids and bases. Plus, there are other classes of problems that you can do with acid and base equilibria. And as for what Ka and Kb mean in terms of relative strengths, they're just like any other equilibrium constants. The larger the equilibrium constant, the further to the right that equilibrium lies, the more that acid or base is doing its thing. So, just to talk about some acids, a strong acid, hydrochloric acid, sulfuric acid, something like that, the Ka for those lies so far to the right they can't be measured. It's, like greater than 1,000, greater than 100, just very, very large. Acetic acid, vinegar, is a weak acid with a Ka of 1.8 times 10 to the negative fifth. It lies very far to the left. Ammonium is the conjugate acid of a weak base, and its Ka is 5.56 times 10 to the negative 10th. So it's even weaker than acetic acid. It's incredibly weak. It's a very poor acid. So just know that you can judge these things by the size of the equilibrium constant. You can judge how strong the acid or base is. And in similar fashion, ammonia has a Kb of 1.8 times 10 to the negative fifth. So it's a weak acid. It's much weaker than, say, sodium hydroxide, which has a Kb greater than 1,000. And there is one more way to measure the relative strengths of acids and bases, and that is ionization, or percent ionization, excuse me. Percent ionization is just how much of the original substance has ionized. So, for example, we have a random acid, Ha, at 1 molar concentration has a pH of 3. What is the percent ionization? Now, percent ionization is defined as the equilibrium concentration of H plus divided by the original concentration of Ha. So, what is the equilibrium concentration of H plus? Well, pH is 3, so the H plus concentration is 10 to the negative 3. Now, I've drawn out an ice table just to give you your first glimpse of the fact that for most weak acids, if the, remember, negligible, so it's not your first glimpse. You saw this back in chapter 13. But just to remind you, I should say, that you can ignore the change in concentration for a decently concentrated weak acid or base. Now, the other thing we can ignore, something you haven't seen before, is that you can also ignore the H plus or OH minus that has been produced by water for the most part. The equilibrium concentration of H plus and OH minus in neutral water is 10 to the negative 7th. That's a very small number. And here we have pH of 3, so it's a concentration of 0.001. And that is 10,000 times bigger than the concentration of H plus you get from pure water. So we can, in fact, ignore that as well. If the pH is about 2 away from neutral, so 5, below 5 or above 9, you can definitely ignore the auto-ionization of water. It's only when it gets really close that water starts to become significant. In any event, percent ionization is H plus over HA sub 0, and HA sub 0 is equal, more or less, to the equilibrium concentration of HA. And in this case, it's 0.001 divided by 1 times 100. So this particular acid has a percent ionization of 0.1%. Now, we go back to the previous slide, you'll see, we go back to the slide itself, not the previous slide, you'll see that I have another example on tap. What is the percent ionization you're going to get for acetic acid, which has a Ka of 1.8 times 10 to the negative fifth. Now I'm going to go ahead and take advantage of this to show you something about percent ionization by doing two quick examples of equilibrium problems. Ice tables. Alright, so on the left we have an ice table for acetic acid at 1 molar. On the right we have an ice table for acetic acid at 0.1 molar. Now they look very similar. Change is minus x plus x plus x. Equilibrium is 1 minus x, x and x, versus 0.1 minus x, x and x. Okay. In both cases, x is going to be negligible compared to the initial concentration, so we can just go ahead and cross those out. And now we find x. Ka equals 1.8 times 10 to the negative fifth is equal to, over here on the left, it's x squared over 1, and on the right, it's x squared over 0.1. It's just the equilibrium concentration of acetic acid. And so, when we solve for x, here on the left, we get 4.2 times 10 to the negative third, and on the right, it's 1.3 times 10 to the negative third. We have a higher equilibrium concentration of H plus when we start with a higher concentration of acetic acid. No surprises there. Now, percent ionization. It's just the equilibrium concentration of H plus divided by the initial concentration of the acetic acid multiplied by 100, which on the left gives us a percent ionization of 0.42%, and on the right gets us 1.3%, about 3 times as much. And that's the point I really wanted to make. The thing I don't really care for about percent ionization is that it changes depending upon the concentration of your acid. I much prefer to work with Ka or Kb, the equilibrium constant, because that actually is a constant depending on the temperature. But percent ionization is still something that shows up from time to time. Some people like it for some reason. Those people are weird. I think they're freaks. I don't like them. But what you gonna do? You guys need to know it, so there you go. And the final thing we're covering for this video is the strength of conjugates. Okay? Remember, every acid, or weak acid, has a conjugate base. Every weak base has a conjugate acid. And we can determine the strengths of those based on the strengths of the original acid or base, and we usually have to. We record the strength of acetic acid, Ka equals 1.8 times 10 to the negative fifth. We don't record the strength of acetate as a conjugate base. We just don't. But it is really easy to figure out. So here we have our two reactions. Okay, here's the weak acid, Ha plus H2O goes to form H3O plus A minus, but its associated Ka. We also have the conjugate base. Acting as a base would be A minus plus H2O goes to form Ha plus OH minus. They're very similar reactions, but they're not the same reaction. It's not just the reverse reaction. Okay. When the conjugate base is acting as a base, we treat it as its own thing. Okay. And it has its Kb. Now, the really neat thing is what happens when you add these two reactions together. The Ha appears on both sides of the arrows. It cancels out. The A minus appears on both sides of the arrows, and it cancels out. And what we're left with is 2H2O goes to form H3O plus OH minus. The auto-ionization of water. And of course it has its equilibrium constant Kw. But what you might not know is that when you add two equilibria together, the equilibrium constant for the sum of those two reactions, the equilibrium constant is equal to the product of their two equilibrium constants. So, in this case, Kw is equal to Ka times Kb. Or to put it another way, Kb equals Kw over Ka, or 10 to the negative 14th over Ka. So if you know Ka, you can calculate Kb. Or if you know Kb, you can calculate Ka, because Ka is just Kw over Kb. Or, and this should look very familiar, pKa plus pKb is equal to 14. pKa, pKb, those things are used fairly often. They're, almost as common as the Ka and Kb, because they show up in some important equations as well. So let me go ahead and show you some examples. I know I've gone over 15 minutes. I promise I'll be done with this pretty quick. And our first example is acetic acid with Ka of 1.8 to the negative fifth. Its conjugate base is acetate with a Kb of, well, that's Kw over Ka, or 10 to the negative 14th divided by 1.8 times 10 to the negative fifth. So its Kb is 5.6 times 10 to the negative 10th. That's quite weak. Now, let's go ahead and compare that to bisulfate. There's some space over here. HSO4 minus has a Ka of 0.01. It's the conjugate base of a strong acid, and it still has a fairly respectable Ka for itself. Its conjugate base is SO42 minus, the sulfate ion. And the Kb for sulfate, well, that's 10 to the negative 14th divided by 0.01 is 10 to the negative 12th, is even weaker. And as we head out the door for this lecture, I wanted to leave you with that rule of thumb. The stronger a weak acid is, the weaker its conjugate base will be. And the stronger the weak acid, the weaker the weak acid, the stronger its conjugate base will be. And the same is true for weak bases. A strong weak base has a weak conjugate acid, and a weak base has a stronger conjugate acid. Okay, so you have a way to calculate it, and you have a good rule of thumb. And with that, I'm going to go die for a couple hours. See you Monday.